Hello. In this unit, we're going to continue the analysis of stochastic differential equations, and we're going to calculate some stationary distributions of the SDEs that come out of stochastic gradient descent. And that's going to give us a clearer understanding of what it means to talk about the learning rate acting as temperature. So this is where we sort of left off. The stochastic differential equation is defined by this update for a finite delta t, where we've got a change due to the expected gradient, due to the true gradient, and a change due to the stochastic nature of the gradient estimates. And as we're holding the learning rate constant in this formulation, this doesn't go away, right? So there remains noise. It's not gradient flow. So we've got these two components. One is the gradient flow component, and one is the stochastic component. Now, our parameter set is changing. There are two sources of this change. One is the gradient flow, right? So the gradient flow is influencing the density, right? You think of this as a continuous density, and there's a continuous flow corresponding to the true gradient. There's also a flow that's induced by the stochastic noise term. So this is a zero mean random variable. So why does that induce a flow? Well, what happens is if you start with a very concentrated density over the parameters, each particular value undergoes a stochastic transition, and since each particular value is undergoing a stochastic transition, unless the loss function is driving it to be compressed, that will naturally spread, right? Each vector is randomly jittering, so the distribution will spread out. Now, to analyze locally what a flow is, all you do is you look at the rate of change of the probability density. So in a neighborhood, you've got a high density place and a lower density place. And if both of those are undergoing stochastic motion, there's motion from the high density to the low density and from the low density to the high density. But there's more mass in the high density than in the low density. So you get a flow from the high density to the low density. You get a flow down the density gradient due to this, due to the noisy motion of all. Think of these as a bunch of little particles. Due to the noisy motion of all those particles. So this is a kind of diffusion term. So there's a gradient flow and a diffusion flow that is diffusing down the gradient density. So the gradient flow. So we've got this continuous density P of x. The gradient flow goes down. Goes down the gradient, follows the gradient. So we've got a flow that's proportional to the density at this point. The amount of mass moving from this point is just the density at that point times the gradient, which is the gradient flow direction that mass is moving. So there's a gradient flow equal to this. There's a diffusion flow, and I've got an appendix of 3 slides at the end of this thing that I'm not going to cover, that shows in a kind of physicist argument that the diffusion flow is proportional to this quantity, where this is the gradient. This is the gradient of the probability density. Now, the analysis I'm about to do is going to be in terms of a single parameter. So I should have said that at the beginning. So let's consider the case where we've got a single. This is just one. X is just one real number. So that this is just the derivative of that number in x. Okay, so a stationary distribution, in a stationary distribution in one dimension, these two flows have to be equal, right? The flow due to the gradient and the flow due to the diffusion have to cancel out. The sum of these two flows has to be equal. And if we set the sum of these two flows to be equal, we get this equation. This is the gradient flow, which is proportional to, so I've introduced this constant of proportionality, is proportional to this expression. This is just the noise in the Gaussian of the equation. And and that has to be equal to the density times the gradient, which is the derivative of the loss with respect to x. Okay, so it's important that the gradient is the derivative of the loss with respect to x. And this is a differential equation we can solve. So we're solving now for a stationary distribution where the two flows are equal. So I just write this differential equation, the dx cancels. I move this p over here and this over here. And now I've got dp over p, and I integrate this. dp over p integrates to log p. This just integrates to minus the loss plus some constant. And I can exponentiate both sides, and voila, I get the Gibbs distribution. In one dimension, we get the Gibbs distribution. And not only do we get the Gibbs distribution, but it's very clear in the Gibbs distribution in physics, this would be KT, Boltzmann constant times temperature. Here, the learning rate, eta, is exactly acting. It's in exactly the place in this equation that you would see temperature. So eta is, in some sense, literally temperature in one dimension. But let's do 2 dimensions. In 2 dimensions, it breaks. So let's take the 2-dimensional case, and let's do a super simple case. So I'm going to say I've got a 2-dimensional loss function that's just the sum of a loss in x and a loss in y. And furthermore, I'm going to let the x and y gradients be independent. So we really have, if we're minimizing this loss, we're really doing, or we're doing SGD on this loss, the 2 variables are acting completely independently, right? The gradient update on x and the gradient update on y are independent of each other. And that means that we're going to get a stationary distribution for x and a stationary distribution for y that are given by the previous analysis, because these are both one-dimensional cases and they're independent of each other. So that means that the stationary distribution on xy is going to be just, they're independent, so it's just the probability of the 2 stationary distributions, and you can then write it this way. Okay, so in 2 dimensions, where x and y are independent, we get this. Now remember, the loss function was just the sum of these 2 losses. But this now breaks because there's no reason the noise in x should be the same as the noise in y. The stochastic, the variance of the gradient estimated in x can be different from that of y. So now this distribution, this has 2 temperatures in it, right? So you cannot write this as the loss over a single temperature, and it breaks. Nonetheless, this is going to be, I'm going to use this in the next unit to motivate RMS prop, or at least to relate this theory to something called RMS prop, a particular adaptive SGD algorithm. Now, this equation turns out to be reasonably general. So, oh, sorry, I forgot about this slide. I just want to look at this equation and point out, I mentioned that this is going to be related to motivating RMS prop. If I change the learning rate in x and the learning rate in y in this equation, so if I use a learning rate in x, which is a fixed learning rate divided by the variance in x, and the learning rate in y to be a fixed learning rate divided by the variance in y, I get this equation. And I can force this to be Gibbs by defining learning rates that are specific to the parameters, parameter-specific learning rates, where I divide by the variance of the noise in that parameter. And that's what's going to be related to RMS prop. We'll talk about it. It's not a clean, definitive derivation of RMS prop, but it gives some intuition or some understanding of why you might want to have different learning rates in different parameters. We can do a slightly more general analysis instead of this very special case where we have a loss that's the sum of 2 losses on the 2 variables independently and independent noise. We can just consider the general case of locally constant noise and locally quadratic loss. And this you would sort of expect this to happen near a local minimum. At a local minimum, it's reasonable to assume there's locally a quadratic loss function. And since the loss function is 0 there at the local optimum, and the noise is not 0, the noise is much larger than the loss, and so we can sort of assume a constant noise over that basin. And in this case, we can simply work in a coordinate system. You can always choose a coordinate system by looking at the eigenvectors of the Hessian. You can always choose a coordinate system such that in that coordinate system, this quadratic basin, the Hessian of that is the identity matrix. So without loss of generality, you can normalize, you can sort of do a Hessian normalization of the coordinate system and get a loss function that's whose covariance matrix is just the identity function. And if you work in that coordinate system, you can measure all of your, if you put all of your coordinates in that coordinate system, you can measure the variance in terms of coordinates that are aligned with the eigenvectors of the noise. So take the covariance matrix of the noise, take its eigenvectors, but assuming that the loss function is just the norm squared of the coordinates. And that analysis that I just gave in that case, where you've got an isotropic, nice identity covariance loss function, produces this distribution, which is again not a Gibbs distribution because it's got a different temperature parameter in each dimension that depends on the noise. So this expression is quite general, but it's not Gibbs. Okay, I'm going to stop there. Thanks.